Very well. So Venema takes us into chapter 5, and he moves us out of the world of neutral geometry. Whoa, that is not okay. He moves us out of the world of neutral geometry and into the world of Euclidean geometry. So for the next few sections of our text, for the next few discussion periods together, we will assume Euclid's parallel postulate. We will assume that given a line and a point knot on that line, there is exactly one parallel to the given line through the given point. That will be our assumption. Because that is our assumption, all of the statements that we've looked at previously that were equivalent to Euclid's parallel postulate, those are theorems in Euclidean geometry. Every single one of them. The converse to the alternate interior angles theorem is a theorem in Euclidean geometry. If I have two parallel lines and they are cut by a transversal, I know for sure that the alternate interior angles will be congruent. In Euclidean geometry, the alternate interior angles theorem is true, and its converse is also true. Euclid's fifth is also true. If two lines are cut by a transversal and those interior angles, alpha and beta, add up to less than 180 degrees. If alpha plus beta is less than 180 degrees, then those two lines have to meet on that side of the transversal. Euclid's fifth is a theorem in Euclidean geometry, which should really not be a surprise. If L and L prime are parallel lines, and some transversal intersects L, that transversal must also intersect L prime. This takes us all the way back to high school. When you draw that transversal and it hits the first line, you never give it a second thought that it's going to hit the second line. Of course it does. Yes, that's Euclidean geometry. Similarly, if you have parallel lines and you bring in a transversal that's perpendicular to the one, well, not only does it intersect the second line, it is perpendicular to it. That is standard Euclidean high school geometry. There are others. The whole business of if I have K parallel to L and M is perpendicular to K, and N is perpendicular to L, then either M and N are the same line or they are parallel lines, because we're going to get a perpendicular here, which means we're going to get a perpendicular here, we're going to get a perpendicular here, which means we're going to get a perpendicular here. M and N must be parallel because those are right angles right there. This, by the way, is how you get rectangles to exist. As soon as you draw a rectangle, you are in Euclidean geometry. Neutral geometry doesn't know of rectangles. Euclidean geometry does. I'm sorry. Hyperbolic geometry doesn't know about rectangles. Euclidean geometry does. If L is parallel to M, and M is parallel to N, and L and N are not the same, then they must be parallel. If you use the hyperbolic parallel postulate, you can't talk about transitivity of parallels that way. It doesn't work. It just doesn't exist. To have transitivity of parallels, you have to have the Euclidean parallel postulate. As we talked about last time, if I have a triangle and the sum of the measures of the angles of that triangle is 180 degrees, if the measure of angle BAC plus the measure of angle ABC plus the measure of angle ACB is 180 degrees, then I'm in the Euclidean plane. Heck, the fact that similar triangles exist tells me that I'm in the Euclidean plane. If I can draw similar triangles, then I have Euclidean geometry. The one interesting thing we should talk about is what the Euclidean plane means for parallelograms. We should talk about what the Euclidean plane does for parallelograms. So let's pretend that ABCD is a parallelogram. There are some properties that are true. For example, triangle ABC is congruent to triangle CDA. Triangle ABC is congruent to triangle CDA. We should think for a moment about why that is true. AC is congruent to itself. Both pairs of opposite sides are parallel, so DA parallel to BC, one pair of alternate interior angles. DC parallel to AB, that's the other pair. And so those two triangles are congruent by angle side angle. It should also be noted that triangle ABD is congruent to triangle CDB. Just drawing the other diagonal. That means that by corresponding parts, AB is congruent to CD, and AD is congruent to BC. These are all things that are not necessarily true in the hyperbolic plane. Not necessarily true. Likewise, opposite angles are congruent. Just from those two congruent triangles, those two pairs of congruent triangles, we get those things true. And the diagonals, this is one of my favorite properties, the diagonals of a parallelogram bisect each other. And that's not hard to prove. We know that the diagonals cross at some point, which I will prophetically name M. So I want to show that DM is congruent to MB, and I want to show that AM is congruent to MC, and I think I can do that. Let's try to prove that triangle 1 is congruent to triangle 2. That shouldn't be too hard. Alternate interior angles are going to make that really easy. Vertical angles are congruent, and opposite sides of a parallelogram are congruent. So I get triangle 1 congruent to triangle 2 by angle, angle, side. And once triangle 1 is congruent to triangle 2 by angle, angle, side, I get all the pieces that I'm looking for. So that's something to keep in mind. In a parallelogram, the diagonals bisect each other. Those are all important results. We use them all the time in Euclidean geometry. You should be familiar with them. Most of what happens when we get to class is going to be just playing with Euclidean geometry. All the things you remember from high school, all of the properties you remember from high school. That's going to be the bulk of our time. I think you will enjoy it. Up next is a look at similarity, but that is up next.